last thing of new material for probability. Today is a little bit of a hodgepodge, but it's like finishing up probability, and then we're going to look at a couple of symbols, really, is what it boils down to. All right, so yesterday we looked at conditional probability, and we filled out tables, and we made our decisions based on the tables, right? Unfortunately, we don't always have complete tables. We don't always have to have a complete table in order to answer these problems. So they have a conditional probability formula. So it's the probability of B given A. We learned that notation yesterday, right? The probability of B given A can be calculated as the probability of A and B divided by the probability of A. So whatever is given, that's my denominator. So it's both on top divided by whatever is given. Okay? So just think about this given bar as your fraction bar. So that's what it's going to be on the denominator. Whatever is given is in my denominator. Okay? So I'm going to show you a problem here. We're going to go through a problem where I'm going to do it both ways, by the table and by the formula. Sometimes the formula is faster. Sometimes I think if it's getting too confusing, the table is easier to break down and look at. So I like both for different reasons. So here's our example. Says, in a study designed to test the effectiveness of a new drug, half of the volunteers received the drug. The other half of the volunteers received a placebo. The probability of a volunteer receiving the drug and getting well was 45%. What's the probability of someone getting well given they received the drug? So let's think about the table first. So we know it says half of the volunteers received the drug, half received the placebo, right? So my totals for the drug is going to be 0.5 and 0.5. We don't have to half. Which we know then that total is 1, right? Right now it says the probability of a volunteer receiving the drug and getting well is 0.45. So I know this cell here has to be 0.45. Now, I can fill in the rest of this row, right? This is like 45% plus what gives me 50%. So that'd be 5% or 0.05. Is that okay? Okay, so let's think about what we did yesterday. I can't fill anything else in vertically. I don't know enough about the people who had the placebo. Is that all right? I really don't need it either, but it says, what's the probability of someone getting well given that they received the drug? So getting well, given they received the drug. That's what we're trying to figure out, right? My given is they got the drug. So what's my denominator going to be? 0.5, right? And my numerator is what percentage of those people got well? 0.45. So I just need to take 0.45 divided by 0.5, which gives me 0.9. Is that right? You're very quiet, are we okay? Okay. Now let's think about this formula. Let's think about the formula side. So we're still looking at the probability of getting well given they had a drug. Right? So my formula says I need the probability of getting well and having the drug divided by the given, which is the probability of getting the drug. Okay, so I'm just writing that out. So we think about it in terms of words rather than symbols. So what was the probability, looking at our, forget the table, look back at our words up there, our text. What's the probability of getting well and taking the drug? 45%, right? Receiving the drug and getting well right here is 45%. That has to be my numerator. What was the probability of getting the drug? 50%. Is it half of the people got the drug, right? So that's 50%. Notice we end up with the same fraction, or same fraction, right? The same ratio. So we still get 0.9, but you have the formula version and the table version. So I like the table version for the visual aspect of it. Sometimes though you don't have a full table and you can do the formula just as well. Absolute worst case scenario, if there's only really two numbers in this whole thing, right? We're talking about 50% and we're talking about, well, when they gave us just the words, forget what conclusions we've drawn. When they give us the words, we've got 50% and 45%. Worst case scenario, make a guess, right? Because we know it can't be 50% over 45%, because that's more than one. And the highest probability is just a 100%, right? In real life, there's not 110%. Like they say give 110% effort, that's not truly possible, right? So the probability can't be over 1. So do you understand what I'm saying? Yes, are you following? No. Okay. All right. So let's build off of that. It says the probability of a volunteer receiving the placebo and having his health improve was 20%. What's the probability of a volunteering improving given that they received the placebo? So the probability of getting well given they had the placebo. Okay, so remember this is the probability of getting well and getting the placebo divided by the probability of the placebo. So what's my numerator going to look like? 0.20, right? And then my denominator, what's the probability of getting the placebo? It was half again, right? So 0.5. So you can divide that out. You get 40% or 0.4. Okay. Are we good with that? Okay. All right, so we're going to practice with that one more time here. Can I change it? All right. It says, in a survey of pet owners, 45% own a dog, 27% own a cat, 12% own both. What's the probability that a dog owner also owns a cat? Okay, so let's start that first sentence there. The probability that a dog owner also owns a cat. So first and foremost, they have to be a dog owner, right? That's the given. The given is they have to be a dog owner. So what's the probability, given that they already have a dog, that they also have a cat? Yes. Okay, so the probability of having both is 0.12. The probability of having a dog is 0.45. So 0.12 divided by 0.45 gives me 0.266 repeating, right? So 0.267, 0.27, however you want to round it. Okay, now the second part says, what's the probability that a cat owner also owns a dog? So they are an owner of cats, right? That's my given. So my given is that they own cats, so what's my denominator going to look like? 0.27, because they have to own a cat. And then, so what's the probability of owning both? 0.12. So 0.12 divided by 0.27 gives me 0.4 repeating. Is that okay? So it's faster than making a table, even if you can only do part of a table, but if you need the table, make a table. Good? All right. This next problem I brought in, dealing with tree diagrams. I'm just going to give you a different way to think about this. It says the college reported that the following based on their graduation data. This is from a college. Said 70% of the freshmen attended public schools, 60% of freshmen who attended public schools graduated within 5 years. 80% of the other freshmen graduated within 5 years. Okay, so what percent of freshmen graduated within 5 years? So we got to think about, we actually have two scenarios, right? We have they went public or they were private. Right, so it said, I can't remember the numbers already, 70% attended public schools. So 70% attended public schools, so what percent then had attended private? 30%, because it has to account for all freshmen, right? All right, from public school, it said that 60% of the freshmen attended public schools graduated within 5 years. So this is graduated, this is not. We'll just call it not, even though that's not what that really says, right? Does that make sense? You graduated in 5 years, did not graduate 5 years. It says that 60% of them graduated. So what percent did not graduate? 40%. Okay, we also have the same thing for the private. 80% of the freshmen graduated in 5 years. So we have graduated and not. We know that's 0.8. Not graduating in 5 years then would be 20%, right? 0.2. Is that okay? So let's first figure it out. It says what percent of freshmen graduated within 5 years? So let's figure out just the public side first. So we have went public and graduated. Public and graduated would be public and graduated would be 0.7 times 0.6. Right? This is public and graduated would be a multiplication problem. Is that okay? So then what about private and graduated? 0.3 and 0.8. Okay, well I have to add those together because they're from two different groups, right? I'm just adding them together, the results. Okay, so 0.7 times 0.6 gives me 0.42. 0.3 times 0.8 gives me 0.24. Add them together, I get 0.66 or 66%. Is that okay? So it's just an and problem. Because sometimes it's easier, there's a lot of information there, so sometimes if you could draw something out to help you, that might help as well, as far as eliminate extra information. Good? All right. Last idea then are just symbols, referring to symbols. So this upside down U here is called an intersection. This says A intersect B. This is an and problem, meaning we're going to multiply. It really just means the probability of A and the probability of B. The U is called a union. Okay, this is an OR problem, meaning it's going to be addition. Sometimes they'll use these symbols, sometimes they don't show up at all in the air test. There's no, we can't find a pattern. Okay, so I just want to show that to you just in case. So we're going to do two problems involving decks of cards. So the first one says probability of red union 3. So union is going to be an OR problem, right? So this is going to be an OR problem. So we're using a deck of cards here. So in your deck of cards, you have 4 suits: hearts, diamonds, clubs, and spades. Yep. The other numbers, well, you have an ace instead of a 1. 2, 3, 4, 5, 6, 7, 8, 9, 10. You have a jack, queen, and king. Okay, that's what's all in your deck of cards. So what's the probability of having a red card? 1, 4. No, not 1, 4. Because there's reds for hearts and diamonds.
1/2.
Is 1/2, right? But I'm going to write it out of 52 because I don't want to have to add fractions with unlike denominators. Okay, because I don't want to have to pull out a calculator by fraction. So I have 26 out of 52 that are red. Okay, how many do I have that are 3s? Wait, 4. 4 out of the 52, right? Do we have an overlap we have to worry about? Did we double count? Yes. Yes, we have to subtract 2 out of 52 because we double counted the 2 red 3s. We have a 3 of hearts and a 3 of diamonds. They got counted both in the red category and in the 3 category, right? All right, so we have 26 plus 4 is 30, minus 2, that gives me 28 out of 52. Last one says probability of red intersect 3. So that's actually an and problem, right? Red and 3. So this is going to be my and problem. Okay, so I'm going to do this mathematically, and then we could actually find this answer without doing any calculations at all. Anybody know what the answer is? How many red 3s are there? 2 out of 52. So our answer has to be 2 out of 52 because it has to be both in both of those categories. Because there are only 2 3s that are red. Okay? But let's think about this mathematically, like how I would compute it. Because we've been doing this and problems, we know it's a multiplication problem, right? So how many reds do we have? 26 out of 52. Okay, times how many 3s do we have? 4 out of 52. Okay, if you multiply that together, I don't remember what it is. We should have 104 out of 53 squared is 2704. Those two fractions are equivalent. If you reduce this all the way, it's 1 over 26. Simplify 2 52nds, that's 1 over 26 as well. Is that okay? Questions on any of that?